Cool. Welcome back. Let's look at ourselves. So I hope that you got a lot out of Leo's lecture this morning. I think one thing that I got out of it is that we need to be really careful about our assumptions. And we need to know what assumptions we're making and how that relates to like what we're actually saying, and be careful to say the things that our observations actually show. Yeah. So does anybody want to, I don't know, share something that they thought about double diffusion or anything else that Leo talked about? Anybody have any profound thoughts this morning, or did you just maybe not have your coffee yet?
I liked Arjun's question. I thought that was useful because I use general circulation models as well. So it's something that I didn't necessarily think about until that lecture. So and then how does that play a role in that? And as well as on stuff on the ocean circulation from deep water formation, like how much does that play a role, especially like in the
Yeah, it seems like so much depends upon these very like local and regional processes that are forming deep water, and maybe the people who study those haven't thought about double diffusion.
There were like polar regions with very minty water as well. I like what you said about it's not about where it matters, it's more about where it doesn't matter.
I think that's always interesting for thinking about like what things that we measure are like material properties, and we can think things like buoyancy conservation, if that makes sense, or like salinity conservation makes sense because salinity is a material property, and like temperature or like energy conservation makes sense, but like buoyancy is not something like that, right? Say that it makes this like a physical thing.
Yeah, I felt like that was the first time I had heard somebody explain like buoyancy and spiciness as these orthogonal I don't know, features, components. I don't know what the word is, but I think it helped. Okay, so what I am hoping to do is hide my thing. I don't think there's much for it to block my slides anymore. Okay, so I'm going to continue to talk about sort of flies in the ointment. So we went over a lot of theory early on in the week. Yesterday we talked about observations and instrumentation, and I think that that continues to this growing sort of snowball of like the assumptions that we're making. And so I'm going to try to recap a lot of that and talk about like how do the assumptions that we make impact the things that we're actually saying, and where are those assumptions specifically sitting, rather like some of them are in theory and some of them are in instrumentation and most of them are in both. And how do we like, and also like as we continue to grow as a field, as technology develops, as theory develops, when can we start to challenge the assumptions that we've had to make in the past? And then yeah, I don't know, you challenge an assumption with an instrument, but does the theory exist to match? Yeah. So I hope that if nothing else, this helps you remember some of the stuff we talked about this week. Maybe I make my slides. Okay. Is that really the next slide? No. Okay. So like I was rambling about, turbulence is complicated. We make a lot of assumptions in order to describe turbulence statistically because it is so complicated, and a statistical description is often more useful than a direct resolution of everything that is going on. But these assumptions simplify the details that we have to understand, and they have the potential to gloss over some important physics, especially if we take them for granted. So just to remind you all of some of those assumptions that we're making, we assume this statistical homogeneity. So that means that the turbulent field maintains a similarity during decay such that it can be fully described by a length and velocity scale. We're assuming isotropy. We've brushed on that one a lot this week, and we'll continue to do so. So we're assuming that the turbulent field structure in a statistical sense is directionally independent. You can measure it from any direction, and you'll be describing the other direction. That is, once you're at the scales of 3D turbulence, that's when you can assume isotropy. So steady state, that the amount of energy being dissipated is equal to the amount of energy supplied to the inertial subrange. And then going a step further than that, we've assumed in some cases that there's this balance between shear production, buoyancy production, and turbulent dissipation. But in a simpler sense, steady state. And so this all leads into this idea that the small scale components of a turbulent field are independent from the mean flow and the larger scale motions by which energy is fed. Okay, that's a lot of words. Sorry. So many words. We're going to start off with isotropy as an example of an assumption that exists both in the theory and the instrumentation. So, sorry, more words and equations. I'm sure we'll get to a picture at some point. So this equation is just energy density, and you can see that it depends upon all three components of velocity. It's a three-dimensional thing, but we can write it one-dimensionally, and this one-dimensional definition of energy density is what we use to describe isotropic turbulence. So you've seen a version of this slide before in Ankita and Andrea and Helen's talk, but we have this term in the kinetic energy, turbulent kinetic energy equation for viscous dissipation. And this part, we don't have a stick of power in this room. This part right here, if we assume isotropy, and that the small scale turbulent motions are primarily driven by vertical fluxes, that's the Z, we can turn this guy into this guy. So that is sort of, just reminding us where this assumption exists in theory. We can do the same thing for the temperature variance equation. So we're assuming that we can express this in terms of one dimension, and then the one dimension we're going to care about is the vertical. And just to dwell on that for a sec, we're also saying that we know that the aspect ratio of the ocean is such that horizontal things are very different from vertical things. So this really is limited to those very small scales where we think that stratification is no longer impacting the flow. That's where we think this isotropy 3 turbulence thing is valid. So yeah, this is the theoretical spectrum that we've looked at a couple different times. Isotropy is assumed in the inertial subrange right there. But that means that this shape, this shear spectrum shape, and the one that, we've seen how our observations give us a shape that we can fit with this guy. But the isotropy assumption means that no matter if you have a cloud of turbulence, no matter what angle you cut a profile through that, your shear spectrum should be the same. And I think about this a lot as somebody who designs shear probes, and then I see people sticking shear probes on gliders, which I'm used to working with profilers, and all of these assumptions are talking about, temperature variation and shear in the vertical. But now all of a sudden you have this thing going through at a pretty horizontal angle. And is the signal that you're measuring a variation that is only at this scale? I don't know. I think, anyway, something to think about. So as I was saying, isotropy is also built into the instrumentation. So these shear probes that we use to measure turbulence at the moment can only measure in one direction. So we do tend to put 2 shear probes next to each other. So we'll have we'll have both components being measured, but at least in this lab, in the processing, we don't treat that like 2 components of a vector. We just average them because it's more for redundancy than for truly resolving 2 components and accounting for that. And usually one of them breaks anyway. So that's the other reason why we have 2. So you've gotten to see this TTV thing, this acoustic travel time instrument. And so the idea behind that, I should have put a picture of the actual thing instead of this cartoon, but we have 3 different components of very small scale velocity from that. So in theory, we would be able to get I don't know, epsilon sub x, epsilon sub y, epsilon sub z. But so far in the literature, nobody has used descriptions of epsilon like that before. So we would sort of have to go back to basics and reinvent the way that we think about turbulence to make any sense of those. Other than just, we could take all of that data and average it and get 1 epsilon from it. And then we have a more robust isotropic estimate. And so, that's valuable, that reduces error, that has a lot of value, but we're close to the point where we're going to have this way to measure on a small scale, the anisotropy, so like the departure from isotropy of these different flows. And I think that we haven't, like, that instrumentation is so new that we haven't quite caught up to realizing that we are going to have to, rework some of the theory in the way that we describe these observations. And so I think that's kind of an exciting place to be. Yeah. So just to talk about some cases where this assumption is violated, or sus. So again, this isn't a different area of the spectrum, but I don't know. Okay, so there's I'll just go to the next slide where you can see which part of the spectrum. So I talked about this a little bit. This -1 slope region of the shear spectrum, where there's still some debate about what exactly the dynamics are that are going on there. A lot of people, some people think it's this layered anisotropic stratified turbulence. So the idea is that we're not at a small enough vertical scale yet where we can ignore stratification. And the effect of that is that because the flow is still impacted by stratification, you get these sort of pancakes of turbulence. So if you were to look at it on the horizontal, you have a turbulent flow, but because in the vertical, it's still at a scale where it's impacted by stratification, it's not fully isotropic yet. It's not fully three-dimensional. And that's why it shows up differently in the spectrum. But now, I don't know, maybe somebody in the room has a better answer for this than me, but I just think about, like, if you have one of these big flat pancakes and you cut a profile through it this way, or if you drive a glider through it this way, I think that the observation you're going to come up with and the amount of turbulence that you're going to see in that same area are going to be different. So I think that's something that we still have to reckon with. And then another case where turbulence is known to be anisotropic, at least the larger scale structures of turbulence, is near topography. You can get these big, like, layered sort of pancake vortices coming out. And so I think near boundaries is another place where we're not, like, as confident in isotropy. And also, who knows? It's kind of like what Leo was talking about, that it's something that we haven't really had the ability to look at, or people just haven't been focusing on. But I think it's something that's worth focusing on, especially now that we are gonna have the instrumentation to, like, observationally have an anisotropy. The anisotropy ratio is something that exists in fluid dynamics. It's like the extent to which a fluid flow follows isotropy. But now that we're gonna have these small scale observations, I think that we can start to figure out where these assumptions are valid and where they're not. Yeah, okay. That's my isotropy spiel. Does anyone have any questions before we move on to other assumptions? Okay, cool. Yeah, so we make these assumptions of statistical homogeneity in steady state so that these are what the assumptions are. So we're assuming that we're self-similar at different scales. As the turbulent flow is decaying, it's going from these bigger three-dimensional eddies to smaller three-dimensional eddies, but that the sort of statistical description of what those look like is the same at different scales. They're just drag the corner, I guess. And then we're assuming that they're time invariant over the scales at which we're measuring. And so because different tools measure at different scales, I think that kind of goes way back to Andrea's talk on Reynolds decompositions, where if you have a signal that's varying, that the mean is varying, you need to be careful picking the time scale that you're averaging over. So this time invariance assumption is sort of similar to that idea, that our spectral estimates of epsilon and chi usually include 2 to 3 seconds of data. And so on short timescales, we think these assumptions are pretty good, that we don't think that the amount of turbulent kinetic energy dissipation or dissipation of temperature variance is changing significantly over a 2-second window. So that's pretty good. But I think that the part where people take it for granted is sort of in the aliasing in the larger scale of the observations. So, like, if you take, if you're interested in turbulence on the scale of the tide, you need to make sure that you have enough observations of turbulence So just being aware that the turbulence is varying on larger timescales than what you're measuring, or so for one profile, one spectral estimate, time invariance is a good assumption, but for example, if you're using a fine scale parameterization, or if you're using coarse graining, or if you have another way that you are estimating epsilon or chi that's using a longer time scale, that's where you might have to think about what is forcing the turbulence. Because if the forcing is varying, then the amount of turbulence is probably varying too.
I have a question.
Yeah.
So when you were saying about the 2 to 3 time seconds of data, how long does at that scale does the turbulent event occur? That makes sense. Okay.
Because it's a statistical description, it's like all of the above.
Sure, okay, yeah.
Like if a turbulent event like the whole, maybe this plays well into this, like which one of these things that's going on in this picture is the turbulent event, you know?
Yeah.
Is like there's secondary instabilities and there's primary instabilities and there's so I don't have a good answer. And maybe we can think about that because like I think Matthew showed this plot too. It's from a paper called Goldilocks mixing that was pretty interesting. So like if you imagine, you know, you have your like kaiki and you have your VMP and you take 3 profiles and you throw it over the boat and then you have to haul it back up like manually. Like which part of this, so this is a numerical simulation of a Kelvin-Helmholtz billow. So this is like the initial overturning and then secondary instabilities start to develop and then the whole thing sort of is just it's re-stratifying, finding a new but there's turbulence like I mean this picture to me kind of looks like the video that Matthew was playing at the end of his talk of the thermistor chain that just has the mixed layer like over time. But yeah, what your 2 to 3 second spectral window could be describing any one of these depending what time you happen to catch the billow. So I think yeah.
Yeah.
This is also kind of one of these like drug lectures. But I guess the point is that if your goal is to describe this event in a way that is statistically significant, then you need to know what time scale your forcing is varying over so that you know how many measurements you need to kind of resolve what the turbulence looks like. So this is another plot from that paper that's just showing like, so this is the normalized time for one of these Kelvin-Helmholtz billow events. And so this is the Thorpe scale, so it's the largest scale of an overturn. So like an overturn would be like if you have dense water over light water, how large is that scale? So you can see the scale of those overturns is just decreasing with time. And then the Osmondov scale, which we've learned about, has this peak in it. But gamma is this mixing efficiency quantity that we've talked about. So like the idea of mixing efficiency is sort of like if all of this energy is going into epsilon, how much of that is going into producing potential energy? So like moving dense water up versus just being dissipated as heat. So the efficiency of the mixing during the lifetime of this billow is changing. It's maximum where there's this circle, so that circle corresponds to this circle, and then the shapes correspond to different time steps. So I think this is another thing where like usually we just assume the gamma is constant because that's all we can do, or you know, yeah, we just choose to. But if it's changing over the life scale of one mixing event, then I guess if it's constant, you would just be assuming that you have enough of these going on over your window that it does average out, that you get things that are at different life scales. But I think this is almost an expansion of the isotropy assumption. Like we're assuming that on the scale of 3D turbulence, things are averaging out to a similar value over the field that we're looking at. But then assuming that gamma is constant is kind of like assuming that you have like enough windows that are at different life cycles throughout your field that you would get a constant gamma. I don't just a cool figure, something to think about for me to ramble about for a couple. Any questions about this before we move on to another example? Okay. So this was a study that was out in La Jolla Canyon, looking at the semi-diurnal tide. So all of these plots are averaged over one tidal period. And so this is showing the shear and the stratification over one tidal period. So stratification and shear, and you can see that they both sort of increase and then decrease. And then this is epsilon from Ellison scales. So this is, we haven't talked about Ellison scales this week, but it's sort of like, we'll talk about Thorpe scales in week 2, but it's another way to look at like larger scale properties of how things are varying in time and assume something about the fluid dynamics and calculate epsilon. I'm not going to try to explain it without any equations, I'm just from this figure, but this is an estimate of epsilon that isn't from direct turbulence observations. And you can see that at this sort of phase in the tidal cycle, when stratification and shear are decreasing, that's when you get the maximum epsilon. So you can think about that in terms of that last figure we were looking at, where there is like there's a history of turbulence. There's like a life cycle of each tidal cycle, and the epsilon isn't the same throughout the whole tidal cycle. It depends like where you are in the overturn. And this actually isn't convectively overturning. This turned out to be shear driven turbulence. So like the tide sloshes up the canyon and causes shear instabilities rather than like a wave breaking on the beach, which is more of a convective thing. Anyway, yeah, so the author has identified these like A and B phases of the tide. So A would be where your shear and stratification are still increasing, and then B would be where shear and stratification are decreasing, and you have more turbulence. So he made this sort of like a phasor diagram. So like Richardson number is the ratio of shear to stratification. So like you are likely to have an instability when your shear is strong enough to overcome stratification. So like the stratification is like resisting the instability, and then eventually the shear is strong enough that you can get instabilities. I guess somebody talked this week about how the critical Richardson number isn't really like, people say it's 0.25, but it like also depends upon the resolution of your instruments. But the author found that the most common value is this value of 2. So the colors are showing epsilon from this estimate. And you can really see that like during this first phase of the tide, you have your slightly higher Richardson number and then a lower Richardson number in the second phase of the tide. And that's when you actually see most of the turbulence. So it's kind of interesting, like people use Richardson number as a way to say like, this is where we're likely to have turbulence. But the whole field, especially if you have like advection, you might see high Richardson number and then expect to have higher turbulence like after that. So this is, I think, just another way to look at like that there really is time variance in like the forcing of turbulence. So we need to think about time variance in the signal that we would see. Even, yeah. It's not like the assumption is really on the scale of one spectral estimate. So like in that case, I'm not saying that that wouldn't be valid in this case. It totally would be. But this is more just to show an example of like turbulence varying over time in a data set. And that if you really want to get a look at the dynamics, you need to take that into account. Cool. Oh yeah. And then this, has anyone heard of a wavelet analysis? Raise your hand if you've heard wavelets or used them. Really cool. It's like a way that you can do like a spectral decomposition. So you can have frequency on the y-axis and then time. And you can see how the amount, picture this as like a bunch of spectra that are stacked up next to each other. So you can see the amount of energy at different frequencies and see how that changes over time. And so this is one tidal cycle, and he's just stacked them up so they're easier to look at. But this is like, I forget how much time it was, but it was several months of data that he's used to make a composite plot. And so over one tidal cycle, you can see that this peak in kinetic energy moves to higher frequencies. So I thought that this was a really cool example of like another way to look at turbulent kinetic energy cascade. So you're literally seeing like this peak in kinetic energy. You can see the energy move to higher frequencies, and then it gets to this sort of transition frequency where very rapidly it moves to higher frequencies. So, and it's not a perfect analogy between scale and frequency all the time, but I think, and for a lot of cases it is. So this could be looked at like an example of looking at the kinetic energy cascade in frequency space using wavelets. So a use for wavelets that I hadn't thought of. Yeah, okay. What time is it? I think I'm going a lot faster than I expected to. Anyone? Yeah, I think we're probably gonna finish early, but does anyone have any questions before we move on to a purely instrument-based complication?
That wavelet was made for over the vertical, the horizontal component. The way that let me get the question. The wavelet, I'm not sure, but there is on you can only calculate it from a vector. I understand. So the way this wavelet is made from the horizontal velocity.
Let me think about that. So
Or it can be made from kinetic energy as well.
each one of these, each vertical profile would be like a frequency spectrum of kinetic energy.
Okay.
And it was from a mooring ADCP, which I actually, that is a really good transition into my next slide. Talking about instrument noise. So like this is also from a mooring ADCP, but from a different canyon. And if you've ever worked with ADCP data, or actually just anything in the ocean, like you get stronger velocities on horizontal scales because there's less resistance. It doesn't have to overcome stratification. So likely when he computed kinetic energy, I don't know if he tried to incorporate the vertical velocities, but they were probably very small and they were probably close to the noise floor. So I would imagine that this is, I don't know if it's a rotary spectrum though. I think it probably is.
It could be along or across the canyon.
I think he probably, and I was a co-author on this paper, so it's kind of embarrassing, but I think he probably used both components of velocity to compute the spectrum.
Yeah, because I understand that when you calculate the wavelet, you can obtain the eastern and the south north velocity. In this case, it's rotated along the canyon to see what is happening in each part of the canyon, along or across.
I think that this is just kinetic energy, so I think
Okay,
it's both components.
Oh, makes sense.
Yeah.
Okay, thanks.
Okay. Yeah, so I was gonna talk about instrument noise kind of as a complication that we have to think about in observations, but also just because it'll probably be useful to you because you're gonna be processing shipboard and mooring ADCP data. So this is just an example of a frequency spectrum of kinetic energy. So this is components of velocity and then a spectrum is squared, and that's why it's kinetic energy. Frequency, and you can see that there's these peaks. So this is the M2 tidal peak. This is an inertial peak. These ones are just harmonics of the tide, but then the internal wave continuum goes down, and you would expect it to just keep going at the same -2 slope, but it actually flattens out, and that's because of the noise of the ADCP itself. So the purple line, I just made like a random data vector to plot like white noise, and then adjusted the level to figure out what specifically I was interested in, like, can I use my vertical velocity data? Because usually from an ADCP, the answer is probably not. But in my case, I was in a canyon and the canyon was like this, and the flow was like shooting up the canyon. So I had an elevated vertical velocity signal and I was able to use it. Because my signal to noise ratio was like 10-1 at the signals that I care about. Anyway, point is that when you get your ADCP data, this is a good exercise to go through to try to figure out where your noise floor is. Yeah, and the scales of turbulence that we care about are like out here. So this is another example of why this isn't the right instrument to look at turbulence, because it's just below the noise floor. So then the noise floor for U and V would be higher. Yeah.
I have a question. So like we're saying like basically when the noise you generated versus the vertical spectrum or the W spectrum, you're saying the cutoff is basically where those two meet.
Yeah, so I'm like looking at I looked at my W spectrum and I was like, I'm not really sure how much of this is noise and how much is the signal. And in the U and V spectrum, it's really obvious where it starts to like flatten out and like asymptote to this horizontal value. And that's where I would put the noise floor for these components. But in this one, I had to kind of just say like, I don't see it flattening out entirely. So I just picked this sort of bottom value and set that as my noise level. But it's a little hand wavy. So like this purple value is just a value that I kind of moved around. And then I was able to say, based on the signal that I assigned to that noise, that I have about 1 centimeter per second of noise in my W data.
Well, and then how do you also know like of aliasing problems within like, the spectrum? I've seen well specifically with my data, you can kind of see where the velocities become too small. This is like geostrophic data, but velocities become too small, and then you see these power spectral signals start coming in, but it's really aliasing it. And I was wondering if you had
Right.
issues with this
So
stuff, or if yeah.
aliasing, in my understanding, and thinking back to, I think I might have TA'd you in data one. So I'm trying to think back to that, which maybe you are too. So I think aliasing typically comes about when you have a signal that is at scales higher than you can resolve, and it's reflected back onto the scales that you are resolving.
Yeah.
So in this case here, because I expect the slope to continue going down at a -2 slope, just because that's like what we know in theory about the internal wave continuum, I wouldn't expect if there's a signal down here that we're not resolving and it was aliased back over here, I would expect that to also be below the noise floor. Where I would think aliasing would be a bigger problem is if there was a big peak like this over here that you weren't resolving, then you would see sort of a shadow reflection of that on the data that you are resolving. So like, what skills do you think that there is something in your data that's going on at scales? Or are you working with model data?
I'm working with satellite data, so it's like a 2 kilometer grid that satellite data is happening at, but we think that there's a lot of noise contained within that, and so yeah, resolving it. It looks like it's happening at like 10 kilometers roughly even, which is much bigger than the window, so that was one of the problems.
So you think that there's an aliased peak at a 10-kilometer?
Well, I mean, there's a couple things going on with it because we're doing assuming geostrophy, but there looks to be a geostrophic signals within it anyways. So then it's about figuring out what is that, convolution that we can use to smooth the data out of. So then when you do this power spectrum raw, it looks like there's these reflections going on. And and it's happening at sizes greater than what we expected for the resolution of the satellite. So
okay. I know that I'm sure you've read it probably, but I know there's a paper where they were able to use an aliased signal from satellite data to measure the internal tide. And I remember Matthew mentioning that in data one. I can try to find that for you if you haven't read it.
I've been going through your guys' notes again anyways. So if it's in the notes, yeah, I'll find it. Yeah.
Were you gonna say something, Arjun, or
No,
I was thinking of SWAT thoughts?
That is.
Yeah.
Yeah.
I don't remember, but I'll try to find it after class. Cool. So I was gonna do a less hand wavy, how do we account for noise in ADCP data? Okay. So this is just zooming in on like internal wave frequencies. So I've drawn vertical lines at like different scales where you'd expect stuff to be happening. And this is actually from a slightly different data set. So it's not the same spectrum as the one on the slide before. This is from like shipboard data. And I was trying to figure out, so my ADCP, if your ADCP data, and I don't know why I didn't just put a raw plot of it, but it looks super noisy. And if you're trying to figure out like, if you want to smooth out some of the noise, but figure out just what is actually noise rather than smoothing out something that's a real signal, because it can be kind of hard to tell when you're looking at a fuzzy plot, like if any of that is signal that I actually care about, or if that was just caused by the instrument. If that makes sense. So like one way to like justify the amount of smoothing that you do on your ADCP is figuring out where the noise floor is and smoothing just enough to remove the instrument noise. So one way that you can do that is make a spectrum. So this is, again, kinetic energy spectrum, which is velocity per cycles per day. or whatever frequency bin you like. So I can see that we're resolving out to like, you know, somewhere between 30-minute and 5-minute scales, maybe like, I think maybe 14 minutes for the bins on this one. So you can use the spectral method to find the noise floor of your data. So if you just see it flattening out to a certain value, you could cut this off and do a best fit of a flat line, or you could eyeball it. I think I eyeballed this one. So you can use this horizontal line, and based on the amplitude that you assigned to your random white noise vector to get this horizontal line, you can figure out what this noise floor is. And then you plug that into this equation. So this is the noise floor that you found, which for me happened to be at 4 times 10 to the negative 6 meters per second squared, right down here. So you plug that in, and then this is the velocity noise that you think you have. So it's the signal that you plugged in to. So if you're generating a random white noise vector to make that flat line, like the signal that I plugged into that purple thing was about 1 centimeter per second random data to make that line. Okay, so that goes in this guy. This is your velocity noise. And then you can figure out what smoothing window to give yourself to get rid of just the velocity noise in your data. So this is kind of different from the other stuff I was talking about in the lecture, but I thought it would be useful for you guys because you're about to be collecting a bunch of ACP data. So based on this, I figured out that I wanted to smooth over 45 minutes to remove 1.1 centimeters per second of noise. And eyeballing it, that kind of makes sense. It's a slightly longer window than 45 minutes, and that's kind of where this noise floor starts to take over from the data in our spectrum. So. Okay. Another weird ADCP thing is that because your bins have a finite size, you can only resolve a certain amount of the signal in the ocean. So this is a shear spectrum, and it's normalized by stratification, so it's given the name Froude. I think Froude has too many things assigned to its name, but that's the topic of it. So the solid blue line is like the GM spectrum. So this is this theoretical shape of the shear spectrum if you were able to resolve everything. And then if I take into account the fact that, let's say I only have 4-meter bins, which is what I had in this scenario, you can see like the amount of variance in the shear spectrum that you wouldn't be resolving because you have finite resolution in your bins. So the dashed line is like what the spectrum is with your, because you're not able to resolve like down to very small scales. And when this starts to matter is, so you'll learn about the fine scale parameterizations in week 3. So maybe this doesn't make a ton of sense yet, and it didn't make sense to put here. But there's a lot of times where we will compare the amount of variance in our observations to the amount of variance in a GM spectrum or in like a theoretical spectrum. And we'll use that to say if we have more or less turbulence than that theoretical spectrum would predict. So if you're going to do that with your ADCP data and you know that your finite bin size is cutting off a lot of the variance in your spectrum, you have to be careful when you're comparing the variance. So a lot of times the safest thing to do is just take like the very first bin of your spectrum and compare the variance there rather than going out to higher scales where the difference is going to be bigger. But the way that you can compute that amount of variance that you're losing or correct for it is with this transfer function, they call it. And I'm realizing that I should have, oh wait, no, I did. It's there in the legend. So this like sync to the 4th times your bin size times your wave number vector is a good correction for finite ADCP bins. So that's the blue line, and then the red line is another correction for because you're taking a first diff, so you're like d velocity dz that you use to compute your shear spectrum. You lose some variance in that computation because so that's another thing that you could correct for before your parameterization. So I don't know if this will be useful to you, but I thought I would throw it in. Yeah, and this is just like at each wave number, how much signal you're losing. Or no, how much of the signal you're resolving. So you've only resolved like 85% of your signal out here at higher wave number. Okay. That last section at the end was sort of just like weird instrumentation ADCP stuff that may or may not be useful to you. But in summary, we make a lot of simplifying assumptions at the level of theory, instrumentation, and data processing. So this was sort of just kind of a summary of a lot of the stuff we've talked about this week. If you've learned anything from this course, it's that like, yeah, it's a messy, messy world of like how we measure turbulence and how we think about it with theory. So knowing those assumptions is important to be precise in exactly what we're observing and what it means. So like we've, I think, touched upon the fact that like turbulence observations are kind of like rare, but they're becoming less rare over time. So you might find yourself in a lab, even if you're not making your own instruments like this lab, maybe you buy them from Rockland, or maybe you get access to turbulence data because we finally get it on Argo floats. So I think the amount of people who are going to be using turbulence data is probably on the increase. And so it's important to know what assumptions are going into that data before we start using it to say things about the ocean. And I'll leave you there. If anybody has any questions, feel free. I think the afternoon is going to be more starting to work on your projects and actually getting into your project groups. So this is the last sort of like content time trying to tie everything together, and then you're just thrown to the wolves and you have to use it for yourself. All right, well, we're only 15 minutes early for lunch, but what time should they come back home? 1. Okay.
We're meeting down there or here?
We'll be here again.
Okay.
Yeah, I think Margaret Lynon was having an all hands meeting, so they kicked us out of our reservation. So
Wow.
okay. It's okay, it's her last all hands.
Yeah, that's okay.